Hi, in this video, we'll talk about the quantum Fourier transform circuit. So the circuit will be based on the lemma that we did last time, and the lemma is on the screen. And recall that in the Fourier transform on a capital N dimensional space, where n is equal to 2 to the power n, so little n are the number of qubits. In this qubit representation of this basis vector, the Fourier transform acts in the following way. It takes this product state over here to another product state, which we see on the right-hand side. And this notation over here is a binary representation of J1, J2, Jn. So for instance, point Jn is equal to Jn. Jn can be either 0 or 1 over 2, whereas point Jn minus 1 Jn is equal to Jn minus 1 over 2 plus Jn over 2 square. So this is the lemma. Now to go from the lemma to the circuit, we'll need certain gates, and the only gate that we'll need is this gate, which is equal to 1 0 0 e to the 2 pi I over 2 to the power k. Okay, so what does this gate do? It'll show that if rk, so these are several gates that are over here depending on k equal to 1 to n. So this will be for k equal to 1 to n. And so Rk acting on ket 0 just returns back ket 0 itself. Rk acting on ket 1 multiplies this by e to the 2 pi I over 2 to the power k ket 1. Right? And what we are going to show is that the Fourier transform circuit is efficient in the sense that if little n is the number of qubits, then the number of gates required to implement this Fourier transform is order of n square, right? So if I write it in terms of capital N, this is equal to order of log n square, right? That's what we are going to show, right? So let's go to the circuit. So I have already written the circuit over here. So drawn the circuit. Okay, so this is the input basis state. And then we have the first wire where the first gate is the Hadamard gate, followed by a control R2 gate, which is over here. So this R2 gate is being controlled by the second qubit. Then again, we will have R3 gate, which is controlled by the third qubit, and so on. And the Rn minus 1th gate will be controlled by the n minus 1th qubit, and so on. So that will be on the first wire. And on the second wire, you will have initially the Hadamard gate, followed by R2, which will be controlled by J3, and so on. And then Rn minus 2, which will be controlled by Jn minus 1, and Rn minus 1 controlled by Jn. And okay, so the number of gates in this wire is n, and then there'll be n minus 1 gates over here, and so on. So that's one thing to be noticed. And then the output is going to be over here, written over here. But notice that it is in the reverse order of what we have in the lemma. So the Fourier transform is this, but we get this in the reverse order. So this is on the top qubit, and so on. So this is not the complete circuit, but to just complete the picture, what we'll have to do is just apply a swap gate. So I'll have to interchange the first with the last and the second with the second last, and so on. So we'll need approximately n over 2 swap gates to do the job after this, right? So let's see why this thing works the way it is. And I'm just going to explain the first wire, and then it will be clear how the output on the second and the third wire come across. So so the input is J1, and the first gate that is applied is Hadamard, right? So what does Hadamard gate do? So J1, and then we'll apply the Hadamard gate, right? So what will be the output at this point after the Hadamard gate gets applied? I claim that it will be 0 plus e to the 2 pi I 0.j1 get 1 over 2 over square root of 2, right? Why is that? Okay, so recall that Hadamard gate takes ket 0 to 0 plus 1 over square root of 2 and takes ket 1 to 0 minus 1 over square root of 2. So indeed, if J1 was 0, then you will get a 0 over here. So this will be e to the 2 pi I, which will be cos 2 pi plus I sine 2 pi, which will be 1, right? So you will get 0 plus 1 over square root of 2. On the other hand, if J1 is 1, then you will get so J1 equal to 1, then you will get 0 plus e to the 2 pi I 0.1 get 1 over square root of 2. Now this is what? This is 0.1 means 1 over 2, right? Because it's in binary representation. So this will be equal to ket 0 plus e to the pi I 1 over square root of 2, which is going to be ket 0 minus 1 over square root of 2. So at the end of the first application of the Hadamard gate will be exactly this, right? So this will be after the application of the Hadamard gate. So we are over here now in terms of the time slice. We are right here, and this will be get 0 plus e to the 2 pi I 0.j1 get 1 over square root of 2. Now what happens is that we apply a control R2 gate, and the control is by the J2 qubit, right? The qubit which has value J2 on the second wire, right? So what happens when I apply? So now we are 0 plus e to the 2 pi I 0.j1 get 1 over square root of 2. And then we are applying a control R2 gate, right? The control is on J2. So what will be the result of this? Well, if J2 was equal to 0, then the control gate does not get applied, so nothing happens. So we get 0 plus e to the 2 pi I 0.j1 get 1 over. So nothing really changes, right? And since J2 is 0, I can write this as J2. If J2 is 1, then what does the control R2 gate do? It doesn't change the ket 0 vectors. This will remain this. And then what it does is it multiplies. So this is multiplies the ket 1 vector with e to the 2 pi I into, so 1 over 2 square, right? Because k is equal to 2 and ket 1. And so therefore, I can write this as get 0 plus e to the 2 pi I 0.j1, and I can add this j2 over here. This is divided by square root of 2. Why? Because I can just take this inside over here, and j1, so this will be 0.j1, j2 will be j1 over 2 plus j2 over 2 square, right? So this gets, okay. So therefore, at the end of application of the R2 gate, you will get 0 plus e to the 2 pi I 0.j1 j2 get 1 over square root of 2. Okay. And then so on. Well, if now we have 0 plus e to the 2 pi I 0.j1 j2 get 1 over square root of 2. And then we have a control R3 gate, and the control is via the J3 bit, right? So therefore, if J3 is 1, again, it will multiply by e to the 2 pi I into J3 over 2 cube. So that will result in 0 plus e to the 2 pi I 0.j1, J2, J3 get 1 over square root of 2. And so on. So if I look at the top wire, therefore, at the end of all the applications of this control RK gates, you will get this output. And then the remaining wires, the second wire and the third wire, can be explained similarly, right? Now, the only problem is, as I mentioned, that the output is coming in the reverse order. So we can apply roughly n over 2 swap gates. So now the question is, how efficient is this circuit? So we have to count the number of gates. We have n gates on the first wire, n minus 1 gates on the second wire, and finally we have 2 gates on the second to last wire and 1 gate on the last wire. So the number of gates is equal to summation I is equal to 1 to n I, right? This will be n into n plus 1 over 2, and then plus the swap gates, right? So this will be plus maybe n over 2 swap gates. And therefore, this is order of n square, right? So it's a quadratic n, or if I write it in terms of the dimension of the Fourier transform, then it is order of log n square. Okay. Recall that the classically Fourier transform or the discrete Fourier transform takes order of n log n. If I do the fast Fourier transform, it takes n log n gates, and therefore it's an exponential. So exponential speed up. One thing to mention is that the way we are measuring the or the complexity of our Fourier transform is by counting the number of gates. we had up till this point, we had counted the number of queries or oracle calls. In this case, we are counting the number of gates. So the number of gates is order of little n square. Thank you.